Record. Okay, so recording is started. And start slideshow. Okay. Can everyone see my screen?
Yep.
Okay, cool. All right. Oh, Auntie's back. Great. All right, cool. We're getting started now. So hello, everybody. Welcome to recitation number 2. This is going to be on computing derivatives. And we had that fun little subtitle in the bottom because influences are going to be a really big part of computing derivatives. But yeah, so my name is Jacob Lee. I'm one of the TAs, and I'm also here with Auntie. I guess say hi.
Hello.
Yeah, we're going to be running recitation number 2. And I'm going to get started first, and I'll hand it over to Auntie in the second part. I guess, yeah. So today, really the goal of today's recitation is to develop a conceptual understanding of the math behind backprop and autograd. And also, we've sort of tooled it to give you some tips and hints for homework 1, part 1. Some of the hints are pretty strong, so I suggest you stick around if you're interested in those. But really just keep in mind that the homework 1, part 1 write-up should be enough to complete the assignment. This is just going to be some more additional context, breadth, depth, some tips, etc. But also in general, understanding this stuff is going to be really important for DL. Like, you're going to be seeing calculus, in pretty much every lecture, pretty much every quiz, pretty much every assignment in a bunch of different papers later on. So even if you don't see it directly, it's going to be an important part of what DL is. And so it's a good idea to understand this content. So kudos for being here / watching the recording. And I guess final note is we'll try to minimize overlap with the write-up to keep this helpful for you guys. Yeah. So if you guys have any questions, just like raise your hand or put something in the chat. We're really happy to help. Just some small requests. Try not to ask questions that are too technical, detailed, niche. I guess if with some exceptions, like if you think it's really important for homework 1, part 1, then totally fine. If it helps your understanding, also totally fine. Or if you spot a significant error, that's also fine as well. But yeah, what I realized when I was writing and researching is that there's a lot of topics and all of them are really, really complicated. And so communicating the essence of them fast is really challenging. So just keep that in mind. And then the second request is try not to interrupt the flow with long questions or too many follow-ups. If you have those, then Piazza or office hours might be best. So yeah, just 2 small notes. Yeah, so the agenda for today is we're going to start off by talking about the motivation for backpropagation. And so we're going to look at the training routine and how it sort of motivates backprop and autograd. And I guess also specifically, we're going to be talking about loss and loss functions, which are very, very important. We're then going to move on to backprop, where we're going to be talking about derivatives, also gradients, and then also the chain rule and its derivation. And then afterwards, we're going to get straight into more direct homework 1, part 1 stuff. So talking about code stuff, talking about math, and also providing you guys extra resources. And then finally, item number 4 would be the example of autograd, which I will hand over to Auntie at that point, and he will cover that part. So yeah, that is the agenda for today. So motivation, training, and loss. So I guess an important question is why calculus? Why of all math topics, why are we talking about derivatives and why are we talking about calculus here? And I think a really key point that's easy to miss if you don't pay attention is that neural networks, training a neural network is essentially an optimization problem. And calculus is used a lot in optimization. And the goal of the optimization is essentially to minimize the loss by adjusting the network parameters. And to see how a neural network does this, we're going to look at a single training loop iteration. So this diagram might look familiar. It was on the write-up, but yeah, we're going to sort of step through it together. So first, there's pretty much 3 stages to training a neural network, where the first of them is forward propagation. And so essentially what happens in forward prop is we provide an observation or a batch of observations to the network. And then the network makes a guess as to what label the observation or observations, in that case it would be guesses, belong to. And then basically that's passed along with the actual true label through a loss function to generate a single loss value. And so if you had one observation, it would be a single loss value. And even if you had a batch, you would aggregate it somehow to get a single loss value as well. And so the loss value is the little orange box on the right over there. So yeah. And after that happens, you basically move on to the second stage, which is backpropagation. We're basically starting from that final box and then moving backwards along the edges. You basically calculate the gradient of the loss with respect to each network parameter. And the reason that we're doing this is we're basically trying to understand how adjusting each of these parameters would affect the loss. Because again, we're trying to minimize what the loss is based on network params. And you can see over here that I've like sort of colored these terms, and that corresponds to which edges they belong to. But essentially, we're calculating, like, not only for this sort of green line over here, we're calculating for all of these as well as all of these, because we want to figure out how adjusting these would decrease the loss. So that's the goal of backprop. And then once we have that information, it's useful for the third stage, which is called step. Yeah, and this, the third stage specifically is called step. It's a very specific term that we use, by the way. And so we basically update the weights using the information from the gradients that we calculated. And the optimizer will try to find a way over time with enough observations that the combination of weights will generate the lowest possible loss. So that's basically the job of the optimizer. Yep, and then at that point it repeats sort of over and over and over again in a cycle for as much data slash computation time as you have. So yeah. So I guess one particular topic that I wanted to cover in this area is loss values, because it's something that's kind of underappreciated, but very, very important. And I see some questions. Oh, Andy's got it. Cool. All right, so loss functions and loss values, they're very, very important in ML optimization. In fact, there's some pretty fun research that's seeing like loss functions actually play a huge role in network performance, depending on how you define them. So they're very, very important. Ideally, they should be like, I guess, maybe not ideally, but they're sort of a general metric for evaluating performance in networks. And sometimes you can use the same loss function in multiple different tasks. And what should happen is, by minimizing the appropriate loss metric, you should cause improved performance in your network. And so how the loss function actually defines that is pretty important, because that'll determine what the network tries to optimize for. Any papers on what Jamie mentioned for some loss functions? I'll get back to you guys on that. Yeah, I'll I'll post links or something like that. But yeah. So what I wanted to do is cover an example of cross-entropy loss specifically. This isn't going to be like hyper detailed. Sort of the write-up will cover that, but it's more of just a conceptual understanding of how it works and like sort of visuals to go along with it. So the task here would be classifying dogs and cats. And so over on the left, you can see that I'm passing in a batch of 3 observations, which would be these 3 pictures. And sort of a brief explanation of batches, because I've seen some questions about that on Piazza, is that the reason that we train on batches, which is basically just multiple observations passed into the network at once, is because we're trying to get as representative of a sample of the entire data set in at one time, if that makes sense. Because if you pass in a single observation, it could be that that observation is very unusual. And so your network goes, oh shoot, I'm very wrong, and tries to overcompensate in a certain sense, but then that actually lowers performance overall. And so in the ideal scenario, we would pass in the entire data set all at once for every single forward pass, but just memory-wise, that's intractable. And so what we do is we pass in these batches, essentially, of multiple observations. And so those are the observations on the left. And then basically what happens is the network generates what we call logits, which is basically like unnormalized confidence in each label. And so if you look at the top row over here, basically this number represents the network's confidence that this image is of a cat, like image number 1, which I believe I've labeled over here. Yeah. And which you notice actually the network actually got this one wrong, where it gave dog a higher score, but then this is pretty clearly a cat, unless I'm grossly mistaken. But yeah, the other ones I got correct because this value is much larger and it's pretty confident this is a cat and it's pretty confident this is a dog as well. So yeah. Oh, and just a thing to note, the size representation is accurate. And so there's 3 batches, so 3 rows, and then 2 possible labels, cat and dog. So there's 2 columns as well. And you guys will pretty much see that in general with like simpler, I guess, sort of tasks, like this general shape of logits. But yeah, so next slide, you have the logits, but we also have the true labels that we need to pass into cross-entropy loss. And so these are basically like indices. And so you notice column 0, that would correspond to this, would correspond to cat. And then column 1 would correspond to dog. And so these are sort of just like a condensed notation for where the correct index is. And that's what cross-entropy loss should sort of figure out. But basically what happens is that you pass this in, you pass both of these into the function, and your function should essentially generate a loss value for that, which I believe what it does is it basically looks at the average confidence. It like sort of scales your confidence, but it looks at the average confidence in the correct answer. And so, yeah, I guess it would look at these 2 and then this as well. Yeah, and this is the actual value. I plugged it into Torch, so it's 0.3583 or something like that. Yeah, this is just sort of like a visual guide to how it looks, just so you guys are aware. And then so for after that, it'll just be more intuitive when you guys implement it. So yeah. But yeah, so again, details are in the write-up. There's also many other possible ways to define loss, and like things like circle loss, you guys will deal with in homework 2 part 2. And like CTC loss is another one you guys will deal with a lot. That'll be fun. And you know, again, the reason you want to look at different loss functions is they incentivize and punish different aspects of network training, which we'll sort of talk about in the next slide. But just some notes: loss value is 1 float for the entire batch, and then we like in sort of the raw form, you'll actually have 1 loss value for each observation, but we aggregate it across that batch usually by something like averaging or summing, so that we have a single value that's sort of smoothed across the batch that we sort of backpropagate on. So yeah, and in homework 1 part 1, you're going to be implementing the averaging version. I don't think we'll need to implement other types of cross-entropy loss, but I might stand corrected on that. But yeah. So one interesting question that I didn't really understand for a while, like personally, but makes total sense now, is why do we train on loss instead of accuracy? Because loss is like not really an interpretable number, at least not easily. Like if you look over here for cross-entropy loss, the number is somewhere between like 0 and then the natural log of this number of classes, which is like sort of, I don't know, like sort of confusing. But there's a very particular reason that we do this instead of training on accuracy. And that's because loss functions are much, like, quote unquote, smoother, in the sense that, like, in loss functions, if you have a partially correct answer, it's different from having a very incorrect answer. And so there's sort of a spectrum across which, like, it's better to have less incorrect answers than it is to have like really, really bad incorrect answers, if that makes sense. And so because of that, it can sort of motivate it and push it in a direction of being like more and more correct, if that makes sense. So there's a type of smoothness to that that's better than accuracy for training. But yeah, but also at the same time, accuracy is like a really interpretable metric. And so sort of the compromise that we do, and you'll also sort of do it in your homework assignments as well, then you'll also probably want to do it when you're just training your own networks, is we train on loss and then validate on accuracy. So that'll make the accuracy, like sort of the validation results, much more interpretable, which is quite nice. So yeah, just a note. So in summary, loss value essentially evaluates the network performance, and the lower the loss, generally the better the performance, at least ideally. And so with that in mind, we can say that our goal is to modify network params to lower loss in order to increase performance. So yeah. And that brings us to backprop. So we're going to talk about backprop now, specifically derivatives, gradients, and the chain rule. And so just a recap of where we are, we got the loss value, blah, blah, blah. And we're at the second stage. We're actually not going to talk about step much today, but just be aware that it's there, and that's where parameters are actually updated. But yeah. So I think one useful topic, and it's one that Professor Bigshaw wanted us to talk about, is this definition of the derivative. I found it actually personally really useful. I didn't know about it before Professor Bigshaw introduced it. But it really helps explain what derivatives are actually doing, and it also helps explain like why the matrices of derivatives have the shapes that they do. And so we thought this would be a useful topic for you guys to sort of have an intuitive understanding of. But yeah, if it's a little bit dry. Okay. So you guys probably have experience with scalar derivatives. That's basically just, like Calc 1, Calc 2, that kind of thing. And then maybe a little bit of multivariable calc as well, so like Calc 3. I actually have no idea how CMU does their calculus, so, but hopefully that makes sense to you guys. But how does all of this extend to matrix derivatives is the thing. And so we're going to talk about intuition and context, and then yeah, I just talked about this stuff, but yeah, hopefully this will be more intuitive and better than just memorizing the properties, which is probably what a lot of people would do. So yeah, just a recap of scalar derivatives. So we have a function here that takes in one input and has one output, where both of them are scalars. And then we have this sort of just function, like this arbitrary function. And our goal is really to determine how changing the input would affect the output. And so when we actually convert that into math, like our goal is actually to find the change in y given the change in x. So this is a very specific mathematical task. Okay. And so what we do is we actually define the relationship between change in x and change in y as this constant, or this variable alpha. You could see like alpha is being multiplied to delta x over here. Yep. And so once you combine these terms, once you multiply them together, you should get delta y is the goal. And sort of the revelation, sort of the trick, sort of the cool thing is that alpha is actually the derivative, which is sort of counterintuitive. And I didn't know about this, but yeah, you can derive the derivative in this way. And so I think the key insight with showing you guys this formula, and notice that I replaced alpha with f sort of colon, I know that's not a colon, apostrophe x, the first derivative essentially. But the key insight behind this is that the derivative is actually a linear transformation. So even for scalars, it would be in sort of like a 1 times 1 sort of matrix kind of sense. And so it's a linear transformation that maps the change in x space onto the change in y space, which is technically the cotangent space, but it's kind of a detail. But yeah, so I think that's a good thing to keep in mind is that you're doing a multiplication essentially when you are calculating the derivative. Yeah. And so another really nice thing about this formula is that it generalizes to higher dimensions very well. And so if we had a function with multiple arguments and a scalar output, and so when I say multiple arguments, I mean multiple variables that we've put into a single vector. That would be the input to the function. You would actually end up using pretty much the same formula form. And so over here, you could see like we have the same thing, change in y is equal to alpha, like bolded, times delta x, which both of these are bolded, just to note that also in lectures as well, we're going to be notating vectors in lowercase, bold, and unitalicized font. So just something to know. Yeah, these are the vectors. This is the alpha vector, and this would be the change in x vector. and that results in a scalar y. And you notice they're actually doing a dot product, which essentially results in a scalar. So that's a pretty important thing to note. We will talk about that in a sec. So yeah, and then this is actually the same formula as the previous slide, but we've just converted it to a more familiar notation. And so yeah, this upside down delta, by the way, is called nabla. It just means derivative in this context. So this would be the derivative of y with respect to this vector x. And you end up with this. Yep. And so to be clear, like this would be the derivative, by the way, this vector over here. I guess to be specific, the full derivative, but yeah. So I guess in summary, for a d times 1 vector input x and a scalar output y, you end up with a derivative that is 1 times d. It's a row vector. And one particular thing to note is that the derivative's shape is actually transposed, turned from d times 1 to 1 times d. The derivative shape is transposed from the input shape, and that'll pretty much always be the case. And there's a particular reason for why this happens, but yeah, just something to note. And the reason for why this happens is because essentially, remember before I said we were doing a dot product, and just by essentially notational convention, what dot products, like sort of by definition, what they're doing is you're taking a row vector and a column vector, and you're performing a multiplication. And so just so that you can have the row column form, otherwise they would be in the same form, you have that sort of like transposed shape essentially. But yeah. So yeah, let me know if that needs some more explanation. But yeah, that's essentially the reason for it. And I guess sort of as a final case, final higher dimensional case, there's vector input and vector output, where you'd have multiple input variables in a vector being passed into a function, and then you receive a vector of output variables. And in this case, notice that there's d input variables and k output variables. You result in a full derivative matrix that's of size k times d. And you notice that each term is essentially, well, I guess each row is essentially looking at a vector scalar derivative, where you have like sort of the partial of y1 with respect to all the x's, essentially move on to the next one, then next one, etc. And that's actually like essentially the same as the previous slides. I think it's the previous slide. It's this one. Yeah, it's the same. It's pretty much the exact same thing as this, but just like sort of stacked on each other. So it's not necessarily more complex. It looks like it is, but it is actually not. So yeah, just a note. So I guess in summary, we looked at 3 cases for the derivative. These will be pretty relevant as well in your computations. I guess especially the term Jacobian, because that's going to come up a lot. And I guess 2 main insights to take away from this is that the derivative is the best linear approximation of a function at a point. And the second is that the derivative describes the effect of each input on the output. And then I should also include linear transformation in there, but yeah, get the idea. So another thing that is important to note as well is the fact that we often interchange the term derivative and gradient. And this was very confusing for me, and I had to do a lot of research, but I think I have an okay understanding of it now. Gradients are actually the transpose of a vector scalar derivative. And so when we refer to gradient, we actually refer to the transpose of the full derivative, those vectors we were talking about earlier. And so they're technically different from derivatives, but in conversation, you'll hear a lot of people sort of interchange the two. And one of the differences between the two is, I guess, in interpretation. And so while the derivative projects sort of the change in output onto the change in, the change in input onto the change in output, that's swapped. I'll fix that in the slides. The gradient is actually just the change in input interpreted in a vector. And that vector will point in the direction of the greatest increase. And so it has that really nice interpretation as like this vector in a space that points towards something. Whereas, and the reason that it has that interpretation is because it's in the tangent space. Whereas I mentioned earlier, the derivative is in the cotangent space, which I have no idea how to visualize. But with tangent spaces, like you could say that this is a tangent line. Like that's very easy to sort of interpret. And so that's one nice thing about gradients as well. But yeah, that's sort of an extra detail. You don't need to fully understand it, but yeah, just so you're aware. Yeah, one particular nice property is that it's great for optimization. So finding the maximum and minimum of a function. And so, as I mentioned before, it's a vector that points the direction of steepest increase. So the magnitude of the gradient vector as well is the rate of increase in that direction. And so like if you have a gradient vector with particularly large values in it, I believe, it indicates that the quote unquote slope is particularly steep in that direction. And so essentially what we do at that point, and what a lot of optimizers do more or less, is if you're maximizing, you follow the gradient, and if you're minimizing, which is the common case, you go in the opposite direction of the greatest increase. So in effect, you go to the greatest decrease. And that is what gradient descent is doing essentially. Yeah. And I guess one final note as well is that one reason we like working with gradients, especially in computer programming, is because if you had matrix shapes that sort of transposed over and over and over again, it's both computationally inefficient and also just kind of a nightmare to deal with because you have to keep track of what's being transposed where and that kind of stuff. So gradients have that really nice property of always being in the same shape as the input matrix, which is quite nice. So just something to be aware of as well. Okay, and so that brings us to the next section, which is talking about the difference between full derivatives and partial derivatives, which sort of motivates the chain rule. So yeah. And so this is actually something I also wasn't like 100% clear on before I actually took DL, is sort of the intuitive reason why there's a difference between partial and total derivatives. And so thus far, the definitions we provided have been for what we call total derivatives or full derivatives, where it's basically you're looking at the impact of all the input variables on the output. And so this should be bolded, but yeah, it's a total influence of the input vector x on y, which would be the output value. And for a partial derivative, you can examine, a subset basically of the input variables, just their influence on y, and sort of isolate that exact influence. And so, for instance, if I wanted to look at x1, if I said the partial of y with respect to x1, then it would isolate x1's influence only on the output. So that's actually a quite useful feature, and that's one that we're going to be using a lot in backpropagation. So just something you're aware of. And yeah, the way that it isolates the influence basically is that it assumes that the other variables are being held constant. So yeah, just something to be aware of. And yeah, and also just a note as well is when you actually solve sort of differential equations on paper, like distinguishing between full and partial derivatives can be very important. We're not going to cover it for now, but yeah, just a note. But I guess one thing to note is that sort of the formulas we've shown you before are very pretty. They're still true, but very pretty. But the issue is once variables within a function actually begin to influence each other, which is what neural networks do all the time, it gets very, very messy, which motivates backprop really. So yeah, we're going to be talking about how things actually get messy. So in the sense that here's an example of a function with two inputs. So you have this function over here, fxz is equal to y. And then this variable z is actually a function in and of itself that accepts two input variables, x and w. And we want to find the total derivative for this function, this should be the partial derivative with respect to x, I think. But yeah, I will verify that. Either way, we want to find a derivative. And what we end up with is a situation where we have we have this visualization for this problem. We call these influence diagrams. And they're really, really useful in visualizing what's actually going on in derivatives. And it also helps you distinguish what partial derivatives are doing intuitively. So these are very, very useful to understand, especially for backprop, because essentially AutoGrad is doing a very similar thing to this. So yeah, So this is a visualization of this problem. What we're trying to do is we're trying to isolate, oh yeah, and these are where the functions are. Yeah, f is this total function over here. But yeah, what we're trying to do is we're trying to isolate x's influence on y. And you notice that x actually influences y in two different ways. It influences y through this path over here, but it also influences z, which influences y. And so there's the second path over here that we need to account for in order to fully isolate x's influence on y. But yeah. And so part of the issue is that there's w here as well, which we don't want to include in our actual sort of figure. And so if we just sort of naively said like, okay, let's take the derivative of y with respect to x, and then we have this other pathway and we sum it, like let's take the derivative of y with respect to z, that wouldn't work because there's also w included in z as well. And so that sort of motivates the chain rule in the sense that like the chain rule will help isolate the influence of certain variables on others. But yeah. And so as I just said, like the chain rule is used to properly account for influences in nested functions. It recursively calculates derivatives with respect to the target. Sorry. It recursively calculates derivatives on the target with respect to the variables of interest, is what I should say. So yeah, so we've already captured these terms in these sort of two terms over here, but we want to also capture this one as well. And we would essentially do that by multiplying this term by the specific influence of x. And so we basically do another derivative multiplied by that. And so that would essentially complete this problem. We've identified what these three sort of edge values are, and we've aggregated them together for a derivative value. And also something to note as well is that this term over here, dz over dx, is actually a full derivative. And the reasoning behind this is because there's no more variables left. And so once we've isolated this edge, like we're over here, there's no more edges left. And so we know for certain that this is the total influence of x on z. Yes, I think that's right. Yeah. And so once you reach sort of the final node that has no more sort of input edges, then you can confidently say this is a full derivative in that sense. But yeah. And so you can see how this could be useful for neural networks. In fact, it's essentially what backprop kind of is we're using it to try to isolate the influences on each weight matrix on the loss. Can you explain what it's taking derivative with respect to an operation? Yes, I will do that in a second. But yeah. And that was a question in the chat, by the way. But yeah, I'll get to that in a sec. So I guess a conclusion on backprop, and then also a note to be aware of. So I guess backprop, in backprop, our goal is essentially to determine how each weight influences the loss. And to do so, we take a partial gradient of the loss with respect to each weight. And I say partial gradient because we don't transpose the output, essentially. But yeah, and in effect, what this does is this isolates each weight's influence on the loss. And to do this, this requires the chain rule. So we sort of came on this long journey defining things to essentially talk about what backprop is doing. And this is the same diagram as before. But also just to note as well, because the diagram doesn't necessarily show it, like I talk about these individual edges in the weights, is that we're actually working with weight matrices. And so to be more precise, like you would work with this as a single matrix when doing backprop. And so it'd essentially just be like that, and you'd have all the values here. So just something to be aware of as well. Yeah. Okay, so we'll go on to the next slide. So I guess starting from now, we're going to be talking about some help and tips for homework 1, part 1. I guess this is the exciting part. I guess first off, we're going to be talking about depth first search and recursion and what those are. Hopefully this should be new for people who haven't taken like a data structures or algorithms class before. Yeah, otherwise it should be good review and also a very big hint for how to solve the problem. And so DFS is needed for AutoGrad, specifically in backward. It's essentially DFS is an algorithm that's used to traverse nodes in trees / graphs / whatever. So essentially anything with vertices and edges, you can traverse with DFS. I believe that's a mathematically valid statement. But yeah, and essentially how we do that is you starting from any node in the graph. So it doesn't have to be that top one over there. We can start from any node. You essentially, as this animation does, you go as far as possible within one branch, then you sort of retreat to where there's another open child, and then you continue down that end and et cetera, et cetera. So you like go back, go back, go back, go back. And that's why we call it depth first, is because you're going as far as possible first along a certain sort of pathway, and then you go back. So yeah. And I'll let this nice animation play one last time, and then I'll move on to the next slide. So there's multiple ways to implement DFS, but our implementation of AutoGrad, and essentially I think what's one of the best ways to do it is to use recursion. And so recursion is essentially when a function calls itself within the function. So like sort of, I guess, Inception, to use the sort of reference, but when a function calls itself, essentially leading to nested calls. And so in effect, what this actually kind of does is it performs like iterative tasks. And so in the same sense that we're like a for loop will repeat instructions, when you iterate into a deeper sort of recursive level, you actually repeat the same step of the same set of instructions again, more or less, which is, so you can actually, it's provable that iteration and recursion are equally expressive in the sense that you can convert programs between both. And just like while loops, you generally need one or more sort of base cases that'll stop the recursion. Otherwise, it'll just continue to go and like take up more memory and sort of crash your computer. And so that's something to be aware of when you implement DFS as well, is you also need like base cases to actually stop the recursion as well. And so I provided a simple example over here. So it's essentially this function, ignore the blanked out lines for now, but yeah, so this function will essentially take, continually make recursive calls until it hits the base case, which is where the input value is greater than or equal to 3. That's this check over here. And then after hitting the base case, it'll just close the nested iteration, or the nested recursions, I should say recursions, all the way back up until it reaches sort of the top level and then closes the function overall. And so that's essentially what this will do. And then I've added some print statements here to make it clear what's happening when, so you guys just sort of have an intuition for what this recursive thing's actually doing. But yeah, so there's three prints essentially. It'll make sense in a second. Yeah. So, yep. So here's an example call as well as a visualization of like intuitive visualization of what's going on. And so over here, I've called this function with an input value of 0. And so it receives 0, sees that it's less than 3, and then makes another recursive call while incrementing that value of 0. And so you can see that it'll go to 1, go to 2, and then when it hits 3, it hits this base case else. And then it starts to just return the value upward, upward, until it reaches the top level. And you can see this is essentially what's happening in this graph, or this diagram over here. We started at 0, we went sort of deeper a level, and then we went all the way until we hit x is equal to 3, which is the base case, and then we sort of returned back up to the top level, sort of closing the recursion. And you can see the final result is, in effect, we've actually modified this input variable of 0 to have a final value of 3. So you can perform like a for loop, like a while loop-ish sort of operation, in effect, by doing recursion. Yep, and here's just an etc. example of where the base case is already met. I'm going to skip over that for now. What you guys are going to need to do is that example of recursion is very simple. You guys are actually going to need to modify that sort of recursive thing to accomplish something else. Specifically, you don't always need to return an output when you're doing recursion. And you can also sort of branch, quote unquote, your recursion, which is where you call functions multiple times on the same level. That's, as you'll see, that's very important for DFS. And so here's another example of a recursion that sort of does those two things that I just mentioned. Essentially what's happening is that at each recursive level, it's checking if the input is a list. And if the input is a list, it iterates over each item in the list and calls this function again. And so if the thing isn't a list, then it'll hit the base case and then basically just do nothing, which I guess implicitly it returns none or something like that. But yeah, essentially there's no return statement and nothing's done with the information afterwards. But this is essentially what would happen is that if you provided this example of nested lists, sort of, you can see there's an outer list and then sort of 3 items, and this is a nested item in and of itself. It'll sort of go to this first item over here, see that it's a list, continue to go deeper, hits 1, realizes it's not a list, goes back up. I'm anthropomorphizing this, but you can get a sense of what's happening over here. And then it goes over to here, goes over here, this sort of pattern. Which you notice is essentially just a DFS. So hint, hint, this is a pretty strong suggestion that this is the kind of thing that you want to do. It's not necessarily the exact form, but it's very similar to what you want to do. But yeah, you can see why recursion would be very useful for traversing sort of data structures, if that's the case. So just something to note. All right, so that brings us to my next help/tip is matrix operation derivatives. So this will be fairly short, and also I want to kind of expand it. I didn't quite finish one of the slides, but this should give you guys sort of a heads up on what the operation questions are throughout the homework. It could be a little bit more complete again, so I will update these slides for you guys. But yeah, so I'm going to give you guys descriptions of the derivatives, also give you guys some stuff in math. So you'll need to translate sort of the math and ideas here to code, but it won't necessarily translate 100% neatly. So just be aware of that, like you have to actually convert it to the AutoGrad framework. But this should be a very good starting point nonetheless, because I give some pretty big hints. Also some general advice as well is when you're implementing a new operation, like I saw some students' code so far where it was pretty significantly different from what the actual torch sort of receives as inputs. And so a big recommendation I have is to make it as similar to the actual torch as possible. And so read the original real documentation for that operation. That'll tell you what parameters are worth saving forward, and also like implicitly tell you what's worth saving in context as well for backwards. And so that's a pretty big hint, because I mean the reason you should do this is because we know that it works essentially. But yeah. So one thing in particular that's been tripping students up, and if you haven't started the homework yet, this will trip you up, is this concept called broadcasting. And so essentially in NumPy and Torch, because we're working with matrices, like higher dimensional matrices a lot, we have to handle these cases. I mean, for convenience, we handle these cases where the matrices aren't exactly the same size or aren't necessarily the right sizes as by the clean definition of matrix operations. And so basically it handles a lot of the edge cases with sizes. And in particular, this becomes useful for problem 2.1, the linear layer, where you need to add broadcasting to add. I believe we need to add broadcasting to multiply as well. Is that right, Auntie?
I don't think you have to do it for the matrix. Are you saying for just normal multiply, or?
Matmul, I think.
I don't think you have to do it for matmul, but.
Okay, cool. Yeah, at the very least, you need to do it for add, so that would be important. And so I provided an example over here of what actually goes on in broadcasting, just to have a quick visual intuition. So in linear, this is essentially what the formula is for that, but X is actually of this shape, W transposed, I've already transposed it for you, is actually of this shape, and then you have the bias, which is of this shape. And then once you perform this multiplication, it should be fairly simple. You're left with these two sort of operations, or these two matrices to combine, but addition isn't really necessarily cleanly defined when there's different shapes. And so that's what broadcasting would actually handle for you. And so I've provided a visualization of that over here. This is an example matrix that's already been combined, so like this step. And you have the bias, which is a different shape. And so what broadcasting is defined to do in this situation is essentially like, in an imaginary sense, it sort of extends downwards with the same values. And then you can sort of cleanly add it to this other matrix over here, which you get your final result. That's essentially what you're going to be doing for linear itself when you modify add broadcasting. But the thing is that's already actually handled by NumPy, which we sort of already allow you to use. And so the trick would be doing it in backwards. And so like undoing it in backwards, I should say. And so what we recommend doing, I haven't seen students do this so far, but it's what we've done, is we've implemented this function called unbroadcast in functional.py. This is like a really big hint, by the way. You can pretty much use the same function if you implement it the right way in pretty much any scenario where you need broadcasting in the AutoGrad framework. And so in the future, I imagine you're probably going to need broadcasting for different types of network components. Like if you have this function set up, it should be really clean to just sort of unbroadcast it back to the original sort of shapes of the inputs to the operation, if that makes sense. Again, Antti, jump in if I say something that is incorrect. But yeah, so I strongly recommend implementing this function. Just a hint, a big part of implementing it is summing along certain axes. So just something to be aware of as well. And a final note is that this shouldn't add to the computational graph. And so we're already in backprop, you don't need more gradients, is essentially the gist of that. But yeah. And so what this would actually look like in a sort of operations backward is you first calculate the gradients with respect to each input, as you normally would, like nothing has changed until this point. But then you actually have to unbroadcast the shapes of those gradients and sort of bring them back to the input shapes, the original input shapes. And so that's where you'd pass the gradients each through this unbroadcast function with certain parameters to unbroadcast it back. So that's essentially how you do it. Yeah. So yeah, strong recommendation to implement this. It'll make everything a lot easier to understand as well. And it's a fairly simple function. It's maybe like less than 6 lines of code. Just the trick is, again, with this homework is concepts. Because I think most questions that we ask of you guys are less than like 10 lines long of code. It's just that they're kind of confusing. So just something to note. Yeah, so add function, sort of operation, blah, blah, blah. So we covered, we had a question in the chat, do we need to implement broadcasting and other functions? I think the answer is no for homework 1 part 1. In the future, it's pretty likely that you will need to, but yeah.
For batch norm, you might have to implement it for some functions, but I don't know if it's necessary. So I guess you'll kind of cross that bridge when you reach it.
Yep. All right, so this is a visualization of an operation.
Sorry, another question. So actually regarding to the unbroadcast one, so could you please provide an example of that? Because it's kind of hard to really understand the purpose of unbroadcast.
Yes, I will do that. I was actually working on a visualization and then it was like 7 a.m. So yeah, I will finish that and upload it. Yeah.
Sure. Thank you.
Yep. Yeah, so here's just basically a visualization of what's going on in the add operation. And it's going to be very, very similar in a lot of the other operations as well. So it should give you an intuition of what's going on. But so you have the normal forward, ignore these terms for now. And you have these like variables that are being combined into this node, and you have an output that's being returned essentially by the forward. In the backwards, you receive this value. You also might have these variables saved. You won't need to for add, but just a note. And then the job of backwards is essentially to calculate both of these values and return them. And so in some operations, you might just have one input node, and in that case, you'll have one sort of gradient to return. But in this case, you'll have 2. And that's what you'll see we provided the add example for you already. So for add, it's quite simple. Both of these are just tensors of 1s in the shape of the inputs. And then I provided some pretty strong, like big hints of the future coming up operations below. So sub and mul and div, I guess you guys can interpret that. And I think it's already pretty big, so I don't really want to talk more about it. Yep, and then there's also a function that you'll probably want to implement as well called matmul, or mult. I think there's the same thing. It's basically just a generic matrix multiplication. But just a note about this is, I should also write this as well, is that dot product is actually a subcase of normal matrix multiplication. You may or may not want to implement a specific dot product. What I would do is I've provided this link to torch.matmul, and they actually list the specific cases when you have different dimensions for inputs. And so what you should do is look at the specific cases that you need for this assignment and try to limit it to those specifically, at least for now, because it might get confusing if you try to generalize. And so there should be a scalar operation. No, it can be generalized to scalar. So question in the chat is, the function div should be a scalar operation. So it can be scalar, but I believe it's on matrices of the same size. Is that correct, Antti? So it would be like element-wise.
Yeah.
Okay, cool. And yeah, and I've also provided a link on Wikipedia for how this operation is defined. And I realized I went pretty long, so sorry about that, Antti. But yeah, and I'll finish this later and provide some more stuff. But that's essentially all I have. I've provided some extra links for you guys. This stuff on broadcasting is useful, and that's it. So, thank you, guys.
So can we ask some question of this recitation? Or you will just end this meeting?
So I think I have some more slides that I'm going to go through, but I think at least I might have some time to stick around afterward to answer some questions.
Can I just ask a quick question before we move on from Jacob's slides? Jacob, in that last bit there, you were a bit confusing. You grazed over this torch.matmul. Can you use numpy.matmul in your torch.matmul function, or are you saying that you have to write all of the actual matrix multiplication code yourself?
So you should be using the numpy matmul.
Thank you.
All right. Okay. Can you guys, Jacob, is my screen shared correctly right now?
Yep, looks good.
Okay. So now that Jacob has kind of gone through what exactly a derivative is, what a gradient is, and then a couple of hints for homework 1 and such, we're going to go through a couple of examples that kind of show that computing derivatives can be trivial, or if not trivial, at least it's pretty straightforward. Okay, yeah, so the first example we're going to go through with influence diagrams. And so this isn't going to be immediately helpful for homework 1 part 1, but this is something that Professor Briksha will use in his lectures. So this is kind of a primer for that. And again, since this is not really immediately useful for 1 part 1, I'll try to go through this one a little bit faster. So here we're going to have some made up activation. It's kind of ugly right here, and here I've kind of shown what this layer might look like. And this example is just going to have 3 inputs and 3 outputs, so x1 through x3 and y1 through y3. And it's going to be a vector activation. That just means that each input affects multiple outputs. And the goal is going to be to calculate the derivatives, or the gradients of the loss with respect to each of the inputs. So the first step is going to be to break things up so that they're a little bit more manageable. The exact way in which you do this isn't super important, but I've just kind of taken all the sums out. And then we don't really need the original formulation anymore. And now we're going to draw the influence diagram for this. So we'll put the equations to the side. And here's kind of this influence diagram up close, and we're going to fill it in. And so first we're going to, for each of those parts, we're going to draw in the influences. So we have A here, and then that's affected by all of the inputs. When we also have B, the sum of those natural logs, and that's also affected by all of the inputs. And then we have the actual outputs, and each of those is affected by its respective input and also by both A and B. So now we're kind of done drawing this influence diagram. And notice X1's different paths of influence. To be exact, it has 7 different paths. And then later on, the loss of this network is going to be calculated, but we're not dealing with that right now. And so the derivative or the gradient of the loss with respect to X1 is just going to be the sum of the derivatives along these 7 paths. And we're going to kind of apply the chain rule at each node to do this. So here we're going to start. And the first edge we're going to visit is from x1 to y1. So we're going to get dy1 dx1. And then we're going to continue this path with the edge from y1 to the loss. So multiply by dl dy1. And this path is kind of finished. Now we're going to go through this other path from x1 to a. So dA dx1. We're going to continue this with the edge from a to y1. So dy1 dA. And then we're going to finish this path with dl dy1, the edge from y1 to the loss. And this path is now finished. And we can do this for the rest of the paths. We've done this for 2. There's 5 other ones. And this is what we're going to get. There's 7 different terms for each of the 7 paths that x1 influences the loss. So at this point, are there any questions, or is there anything that's not clear so far? I can't see the chat, so I guess, Jacob, can you let me know if there's any questions?
Nope,
Okay.
That's good.
All right. So this is kind of, we're kind of done with the influence diagram. The whole point of that was to get these different terms. And now it's time to calculate the necessary derivatives. So here are the equations from earlier. We're going to need those to calculate these derivatives. And we're just going to kind of go through. So we're going to calculate dy1 dx1 from our specification of y sub I. Then we don't have to calculate dl dy1 because the loss is computed somewhere later on. So this is not really in our domain for this activation function. dA dx1 we're going to calculate. dy1 dA we're going to calculate. And then dl dy1 we're going to calculate. Is there another question? Or?
Yes. Sorry. I think shouldn't these be partial derivatives?
Yeah, in a sense. Yeah, in a sense, yeah. Yeah. Okay, so next we're going to have to calculate the rest of these, but a lot of them are repeated or they look super similar. So we'll come up with those. And yeah, a lot of this work we don't really actually have to redo since they look similar. The next thing we're going to do is plug things in and simplify. I've kind of, oops. Yeah. Yeah, the simplification is kind of left as an exercise for the reader here. But yeah. So this can kind of be a little bit painful, but it's algorithmic. First, we kind of break our equations up. Then we drew the influence diagram, and then we wrote out all of those different paths using that diagram and the distributed chain rule. And then we calculate the necessary derivatives, and we plug things in and simplify, which can kind of be a mess, but at the end of the day, it's pretty straightforward, even for more complicated activations. So I guess at this point, are there any questions about this process? Or is anything unclear?
Nothing in the chat.
Okay, so we'll move on. Okay, so now we're going to go on to computational graphs. You can follow the back part on paper. I'll let you guys know when that is, or not. These slides will still be here. And so we're going to do this for a simple MLP. It'll just be an MLP with one TNH activated hidden layer. I don't know if, yeah, so a linear layer and then a TNH activation. And the goal is to easily compute the derivatives with respect to, or the gradients with respect to the weights Wi and the biases Bi. So I've just popped up the canonical equations for this. There's that first linear layer and then the activation. And what we're going to do is unravel these equations into unary and binary operations, so things with just 1 or 2 arguments. This isn't a strict rule, but it makes things easier for us to do. So here we've kind of done that, and we have some intermediate variables. Again, it's just that same linear layer and then the activation. And then we do this because it allows us to reuse rules for propagating derivatives through simple functions like addition, multiplication, etc. So now we're going to step through this code to create a computational graph, and this is kind of a forward pass. So first we'll initialize our variables, so x, and then the weights and the biases. We'll perform this first matrix multiply, and then this next addition, and then this tanh. And so now we kind of have our computational graph. And then this is just kind of a key. Derivatives or the gradients with respect to variables, I'm going to put into a diamond shape, and the variables themselves are going to be the boxed in, and operations are going to be in circles. So at this point, are there any questions, or is there anything I haven't explained so clearly?
Nothing in the chat.
Okay, so here's our simple MLP. And again, just for reference, here's that first linear layer, a matrix multiply, and then in addition. One thing to note is that this formulation is a little bit different from homework 1 part 1, but the same kind of idea applies. I'm also going to add here the derivative of or the gradient of the loss with respect to the output. And this is going to be calculated from our chosen loss function. I'm not including this in the computational graph here, but just for simplicity, but generally it would be part of the computational graph as well. And so this is just kind of a recap of what what Jacob explained earlier. So let's say we have this addition operation. So I guess, does anyone want to say what the gradients of A with respect to the loss, or the loss with respect to A, and or this should be B, would be in terms of the chain rule?
One.
Yeah, so I guess I'm not really asking for all of that yet, but I guess just in terms of like the chain rule, what would it be?
I guess like the symbolic math.
All right, well, I guess I'll give this one. So we have something in the chat. Yeah, so yeah, DL DC times DC DA. So that's what this one would be. And then the next one, which should be B, would be DL DC times DC DB. And so then what would these simplify to? I think Dennis kind of answered this earlier. So DCDA and then DCDB, those both cancel out because they're both 1. And so what ends up happening is add's backward function is just to simply multiply the gradient, or to pass the gradient back unchanged. So there's a question from Yishen.
Hi, so is there a particular reason that we, can you go back to the previous slide?
Okay.
So is there any particular reason that we use the star products between to multiply these two gradients together?
So this is just would be like an element-wise multiplication in this case.
So why we don't use dot products?
So typically we would assume that these would be the same shape, DLDC and DCDA. Yeah, and I guess the addition is element-wise. So when we pass the gradient back, we also have to deal with things in an element-wise fashion.
Okay.
Yeah, so if this was matrix multiply, for example, we wouldn't be using element-wise multiplication for this. Yeah. So I guess, are there any more questions or anything that's not clear? Nope, okay. So we're back at our simple MLP now, and we're gonna perform the graph search from the end and update derivatives as we go. DFS is the easiest, and that's kind of what Jacob demonstrated, so we're gonna use that. Feel free to follow along on paper or not. So first question, if the output is n by 1, then what would be the gradient of the loss with respect to the output? Any guesses?
Would it be 1 by n?
Yeah, it would be 1 by n since we have, yeah. So it would be 1 by n simply because if we have some A with some shape B cross C, then gradients with respect to A are going to have the transpose shape. Okay. So now in terms of the chain rule, what would be the backwards function of this tan H? So here out is just the output of the network. So Z1 and Z2 here are some intermediates, and then out is just the output. Okay, so I guess I'll just write the chain rule up here. So DL DZ2 is just going to be DL D out times D out DZ2. So that's kind of the chain rule here. And then the derivative of the output with respect to Z2 is just going to be the derivative of tan H of Z2. So that would be the backwards function of this tan H. So now any takers for what the shape of, I guess the gradient of the loss with respect to Z2 would be?
Is it n by n?
Not quite.
Okay.
So Z2 is n by 1, and so the gradients with respect to Z2 are just going to be the transpose of that. This is
Okay.
we don't have this in PyTorch on 1.1, but yeah, it would just be 1 by n. Yeah.
Gotcha.
Yeah. Okay, so now we're going to kind of continue downwards by visiting Z2, which is an addition operation. So any takers, I guess we've gone over this before, what the backward function of this would be. Okay, so someone asked what the except in PyTorch and then homework 1 part 1, what does that note mean? So basically, generally the gradients are going to be the transpose shape. So if Z2 is n by 1, then gradients with respect to Z2 are going to be 1 by n. But in PyTorch, so that's kind of how it is mathematically. However, in PyTorch and then also in homework 1 part 1, we don't transpose the shapes, and that's just for convenience. All right, so I guess any takers for what the backward function of add is, and I guess we've gone over this a bunch of times already. Okay, or not.
Just pass back the gradient as is.
Yeah, so the gradient just gets passed backwards since this term kind of gets canceled out, and so we just kind of pass things backwards. Okay, so any takers for the shapes of these two gradients? Huh?
1 by n.
Yep, so they would just be transposed. Again, in MyTorch, or yeah, so in homework 1 part 1 in PyTorch, this isn't going to be the case, but generally this will be the case. They'll be transposed. All right, so now we're kind of done with those, and we're going to continue the graph search by visiting B1. So B1 doesn't have any gradient enabled parents. In fact, it has no parents, and we want its gradient. So its backward function is going to be to accumulate the gradient passed to it, so it'll kind of update its gradient field. Okay, now we're going to continue the graph search by visiting Z1, and this is probably the one that everyone is probably interested in. So any guesses as to what the backward function of matrix multiply would be?
Is it just the opposite of like x gets W1 and W1 gets x?
X gets W1. Yeah, so that's, I think that's right. So yeah, if we have, so for W1, it'll be x1 matrix multiplied by the gradient of the loss with respect to z1, and then for the gradient with respect to x, it'll be the gradient of the loss with respect to z1 matrix multiplied by w1. And these are matrix multiplies. And I guess you can kind of confirm this rule for yourself, but since matrix multiplication isn't a element-wise operation, the chain rule for matrix multiplication isn't going to be just that element-wise multiplication. It's going to be this matrix multiplication. And just for a note, in part one, since the gradients aren't transposed, this rule is going to be a little bit different. We're going to actually swap the order of multiplications, and we're going to have to transpose things as well. And this will be in the slides for reference. So this will, and also I guess just for reference, again, this matrix multiply, you guys should probably use the NumPy thing, so you won't have to implement this completely by yourself.
Sorry, could you
Yeah.
could you explain a bit what is meaning of gradient isn't transposed?
So in mathematically, the gradient will have like the transpose shape of the output. So W1, for example, will have the transpose shape as the gradient of the loss with respect to W1. However, in homework 1.1, and then also in PyTorch, they don't do this, or we don't do this as well, just for convenience. And since the shapes are not going to be transposed, the rules for this backward function for matrix multiply is going to be a little bit different.
Okay. Yeah. Is there any resources that we can refer to figure out why we use this rule here?
I guess I can, or someone can post a proof for how this works on Piazza, and we'll let you guys know. But yeah.
Okay. Yeah.
All right. Okay, and I guess I don't know. We're definitely beating the dead horse at this point. But what would the shapes of these gradients be? So yeah, I guess they'd just be transposed. So the gradient with respect to W1 would be m by n, and then with respect to x would be the other way around. So transposed, yeah. Yeah.
I'm sorry. So you were saying earlier that it wouldn't be transposed though, for convention with PyTorch?
Yeah.
Okay, sorry. Just wanted to make sure.
Yeah. And I'll make that maybe more clear on the slides when we re-upload them. So now we're going to continue the graph search by visiting W1, since we've kind of visited most everything else by now. It has no gradient enabled parents, and we want its gradient, so its backward function, again, is just going to be to accumulate or save the gradient passed to it. And then we visit X lastly. This has no gradient enabled parents, and we don't care about its gradient. Maybe in some applications we do, but in this example, maybe we don't, so we're not going to do anything for X. And so this is kind of everything fleshed out. And here are like the rules for this simple MOP for kind of propagating the gradient backwards. And then we note that we're going to have gradients for nodes that accumulated them. So in this case, this would just be W1 and B. And so we've calculated the other gradients, but we might not necessarily actually need them. So now, what about reusing parameters or intermediate variables? So this will not be immediately applicable for part 1, but I think for homework 2 part 1, and also especially for 3 part 1, it will be applicable. And so the example we're going to use here is a scanning MOP. So this MOP is going to scan across some input. So at this first position, we'll create an output, then at the second position, third position, and then this last position. And it could have a bunch of other positions as well. This is just for example. And so we can think about this as like one big network with shared parameters. So let's create the graph for this. So here we're going to step through the code again. So here we have our initial variables, and we're just going to run through this and create the computational graph. So we run the MOP in the first position, and then the second position, third position, and the fourth position, and we've kind of built up this computational graph. And then these outputs are going to go later on to some other output, but we're not really worried about that. Note that here, unlike the first example, nodes can have multiple avenues of influence. So B1, for example, affects Z2, Z5, Z8, and Z11. And so here's where gradient accumulation is going to be especially important. So let's DFS. So let's say we visit Z3, and then Z2, and then B1. But this isn't going to be the full gradient of the loss with respect to B1 because there's a bunch of other pathways too. So we're going to have to visit the pathway through Z6 and Z5, and then there's two other pathways as well. And so the full gradient of the loss with respect to B1 is going to be the sum of these. And so that's why when we accumulate gradients, we use the plus equals operation to save them. If you look at, so for accumulating derivatives, derivatives are always initialized to 0 or maybe none. And then when we visit a node, we're going to use plus equals to update or the gradient or derivative. The rest of the scanning MOP example is nothing new. We just kind of needed to know that how accumulating works. So I'm not going to go into how exactly the rest of that. Note that we can kind of apply this process to any function made up of smaller differentiable functions. And I guess we've kind of already gone through this, but the process is we kind of create a graph of operations. Then we kind of graph search from the known gradients, and we accumulate them. And then we reutilize reusable and then differentiable operations. And this is just AutoGrad. And so PyTorch builds an implicit graph when you perform operations. 1.1 does as well. And then you can build this graph on paper, to calculate derivatives just as well as you can kind of do this algorithmically. So as an example for how this kind of applies to things outside of deep learning, we can show the graph for like a ray tracer, which is ray tracing 4x3 images. It just isn't very big, but yeah. And so this is kind of what the graph for that might look like. And so for this, what I did is I just found some really short ray tracer and replaced all the operations with PyTorch operations, and then we can kind of see the graph of this. So now for this ray tracer, any inputs that we have, we can actually find out the derivatives of the output of the ray tracer with respect to those.
How did you get that visualization? Like, is there a thing in Torch that allows you to print that, or how did you generate that graph?
So I'll put this. I guess I'll add this to the slides as well. But there's some tool I found on GitHub that you can, I guess, plug into PyTorch, and it'll generate this a visualization for the graph for you. Yeah. Yeah, and so I guess let's say you had some neural network that had the output of a ray tracer, for example, as input. Then you could perform gradient descent over the ray tracer as well, so that gradients could pass all the way through to the input of the ray tracer. And so there's also there's a lot of other applications of this as well. A lot of things in deep learning, let's say there's some process that isn't differentiable, like let's say we're using some rendering engine, then if you can create a version of that is differentiable, that passes the gradients backwards, then you can get your neural network to learn a lot better. So yeah, we could optimize over the inputs of the ray tracer. We could also calculate the derivatives by hand. Since all of these functions are relatively simple, you'll see like there's a bunch of dot products, addition, subtraction, etc. I think that's it for me. So I guess we're open to questions if there's anyone. Questions so far.
Just a quick question on kind of, I'm not sure if this is too specific. Just tell me and I can like take it offline. But like would it be a good kind of analogy to look through the PyTorch documentation, like the way that problem one, homework one is set up? Is it like the classes and the methods, are they very similar to the same simple methods in PyTorch? Like if we look through the PyTorch documentation for one of the methods like linear, would it be pretty similar? Just to understand the general concept.
Yeah, it would be very similar. I think one difference is that how they implement linear, they have the addition and then the matrix multiply, and inside of the same function, so they don't break that up into two pieces. But other than that, a lot of my torch is modeled pretty heavily on PyTorch.
Awesome, thank you so much.
Yep.
I have a question about using NumPy functions. So I asked this earlier in the chat, and it made sense to me, but now that I'm thinking more about it, kind of confused. So when we're doing matmul, we're defining that function. Within that function, we use like NumPy matmul. Yeah.
Yeah, that's what you would do.
Yeah. Okay. All right. Okay. Thanks.
Yep.
So I had a question.
Okay.
When it comes to like first building the graph, there could be like I think in your example, Z was self-contained, right? And then Z was again used recursively by another.
Is this the example you're talking about?
I think it was before this.
All right.
But essentially, like have something like Z is A plus B, and then you use Z in a different equation also.
So I'll go back.
Yeah, so something, yeah, like in these equations.
So we have, so for here, Z.
Yeah, like Z1 is equal to W1x, and Z2 is Z1 plus B1. Is there any way, like if you'd called backward on Z1,
Yeah.
so then you have like all of these gradients. Would we store them somewhere so that the next time if you call like a backward on like Z2, it would use what we've already previously calculated?
So so if you called backward on Z1, then the gradient of W1 would be, or with respect to W1 would be calculated, and then X would be ignored. And so then if after that you called backward on Z2, then W1 would get even more gradient. And that wouldn't, so I guess those gradients would be added together. That's what would happen.
So like I'm asking, would you store these intermediate gradients or something like that you've calculated before, or do you start fresh each time?
So for,
like, would you store it and add to it?
So for W1, it would be stored and add to it, but for intermediate outputs such as Z1 and Z2, those would not store them, so they would pass back something fresh.
Okay, so only the leaf nodes you store.
Yeah, so things that accumulate, so things that are leaves and also require a gradient, those will store and those will get updated, but other things will be starting fresh.
Okay, thanks.
Yep.
And we also had a question in the chat. Would E loss over D loss function always be a tensor of ones? I didn't know the answer to this question.
You said, let me see what it is. Yeah. So yeah, D loss over D loss would always be ones.
Okay, any questions?
Yeah, I wondered if you can give some suggestion for debugging. I just found when I run the code for the autograder, and then the feedback, the error it gives me is just too general, and I don't know where I made a mistake.
So I think that might be better suited if you make like a private Piazza post, then maybe we can help you. And then if there's something you have there that's more general, then we can also add it to the FAQ.
Okay.
Yep. Also some general advice too is you're free to put you're free to put breakpoints within the autograder itself. And so what I usually do is like, if there's a particular case that I'm failing and I don't know why, I'll put a breakpoint right there and then just read what the variables are. That'll give me a pretty clear sense of why it's failing and at what step, if that helps. Yeah.
Okay, I'll do that. Thank you.
So, can you hear me?
Yep.
I have a question. So in this example, let's say x dimension was k by m, not 1 by m. So the output dimension should be k by m, right?
Yeah.
So yeah. So when we do the back propagation to calculate the gradient with respect to b, so we should do the unbroadcasting.
Yeah. So if x had was batched, then it would have some extra dimension, and so then z2 would be 2-dimensional, but b1 would be 1-dimensional. So z2 would have to unbroadcast that gradient before it passed it to b1.
So should we just sum up all the elements along the axis where b is being broadcasting to unbroadcast, like to calculate gradient?
Pretty much. Yeah.
All right. Thank you.
Yeah.
Big hint. Big hint.
Yeah. I got another question. Although Jacob said he will put more resources later, but I wonder. Oh, okay, can you go back to the slide of math multiplication?
Is this in my slide deck or Auntie's?
Sorry, could you go back the slide for matrix multiplication, which includes the equation of how to calculate in the gradients?
So this is in my slide deck, not Antioch's?
No, I'm sure.
Okay.
No, I think it's his slide. Yeah.
Okay.
So we're going backwards. Okay, so here.
Yeah, this slide. So I'm confused why sometimes we use the element-wise multiplication and sometimes we use something like this, the matrix multiplication, to calculate the gradients.
So
could you explain a bit? Yeah.
So for addition is or multiplication or normal multiplication, those are element-wise operations. So then the chain rule is going to be reformed element-wise. However, matrix multiplication is not an element-wise operation, so the chain rule is not going to be element-wise. And the full proof for the backwards function of matrix multiply, I guess we'll post that later on Piazza.
Oh, so when the operation is doing something likely-wise, then we calculate the gradients likely-wise. Otherwise, we'll not do that, right?
Yeah.
Okay, thank you.
Okay, I don't know. Are we out of questions?
I'm fielding a question in the chat. Maybe you could just, because it's pretty general, but
okay.
Yeah, so the person's asking, is homework 1 part 2 due later than is it due earlier than homework 1 part 1? Question mark. And then also, if so, then how do we do, like what order should we do the homeworks in?
Okay. So I think so there's 2 deadlines for homework 1 part 2. There's the early submission deadline, which I think is the 16th. And then there's the final deadline, which I think is the 27th. And both final deadlines for 1 part 1 and 1 part 2 are due on the 27th. But you should have something in for the early deadline for 1 part 2. And for 1 part 2, you can just, I think there's like a sample submission and you can just upload that And I guess it's probably also a good idea to do the quiz as well by that date. So other than that, it's kind of up to you in which order you do it, but you probably want to get that early submission deadline. And yeah, they're independent.
Still have some stragglers here. I guess if we don't have any more questions, we can move to Piazza. Also, I have office hours later today if anyone wants to come, but yeah. So thank you everybody for coming. All right, stop the recording.